Give us a hand up.
Ladies and gentlemen, please welcome to the stage Deputy Director, NASA Jet Propulsion Laboratory, Lieutenant General Larry James.
There's always that voice from the cloud that you never know where. I'm looking at, where is this guy? But anyway, thank you all for attending this year's Pickering Lecture. It certainly is a great event for JPL. It's a great event for AIAA, and frankly, in a long line of distinguished speakers, I think we have another home run tonight with Jamie Bach. It's been an honor for us to see all the great things that he has done and his team has done really over the past few years in the area of cosmic background radiation and discovering and understanding what's going on there. Jamie is a professor of physics at Caltech. He is a senior research scientist at JPL. He received his bachelor's in physics and mathematics from Duke University and his master's in physics from, and master's and PhD in physics from Cal Berkeley. He has been focused on looking at distant, dusty galaxies in cosmic microwave background radiation, using bolimeter arrays to do that during much of his time at JPL and Caltech. And really over the last year or so conducted some measurements down in Antarctica with a system called background imaging of cosmic extragalactic polarization. Say that 5 times quickly. But it's called BICEP-2, and frankly have made some very important discoveries about the early cosmology of the universe that as we work through the scientific proof of all that from various other sources, really could be game-changing in terms of our understanding of how the early universe was formed, how gravitational waves propagated during that time, and to quote Scientific American, could be Nobel Prize worthy if all of their results are proven out over time. So pretty important from a cosmology perspective. Jamie has spent a lot of time with his team developing this capability and actually doing the experimental testing that collected the data and then analyzing it. And it truly is a treat for us to have him here tonight. If you read the LA Times, the New York Times, this discovery was on the front page of the New York Times back in the March timeframe. So I think that shows you kind of the heft of the work that they have been doing as a team. So Jamie, welcome. Thank you for joining us this evening, and we look forward to hearing all about BICEP-2 and the work that you and your team have been doing.
Thank you very much for the kind introduction, Larry. Turn it down a bit. Yeah, so I'm going to tell you about our measurements of the early universe. And when I mean the early universe, I mean the very first moments after the Big Bang, the cataclysmic explosion that brought our universe into being. Now, here at AIAA, you may be familiar with experiments and endeavors on a grand scale. And this is not such a thing. This is a small experiment. Just to give you some idea, this project called BICEP-2 really had its beginnings around 2001. And since that time, we've had about 50 scientists involved in this project, many of them in their 20s and 30s. The key people really in this project are graduate students and people just out of their PhD. And this has been a fantastic team experience. So I'm proud to come here representing really one of the greatest science teams I've ever been involved with. It's also perhaps clear from this photograph that we've gone to the ends of the Earth to do this measurement. This is a picture of our experiment around sunset at the South Pole. Now, the spirit of adventure here in this experiment is to ask the question, how far back can we see what happened at the very beginning, at the dawn of time? And this spirit of adventure is not a new thing. We as humans have been asking these questions for some time, and I love this woodcut, which is from before the turn of the previous century, and it really conveys the spirit of our experiment. And as you can see here from the artwork, the question is, what if we could see beyond the stars? What wonders would we see? And you might ask the question, how far back can we see? Now, there are some details in this woodcut that they don't have quite right. Now, and one of those little details is the light travel time. Okay, so when our explorer there looks at the tree, he's not seeing that tree today, he's seeing that tree 10 nanoseconds in the past. Okay, so that's a pretty small effect. But if he looks at the moon, that starts to be noticeable. Look at the sun, you're seeing the sun 8 minutes in the past. Well, the distance scales we're talking about in cosmology are so enormous that this light travel time becomes appreciable. And so we're not only just seeing how far back we can see in distance, we also get to be historians because we're seeing objects back in time. Now, if I ask how long ago do I see the nearest stars, I'm seeing them a few years ago. Now, another detail that's missing from this woodcut is there's no galaxy. Okay? People didn't know about the galaxy at this time, but of course we live in an island universe, and if we look at stars across our galaxy, we're seeing them tens of thousands of years ago. If we look at the nearest galaxy, it's millions of years ago. And if we take a powerful telescope, like the Hubble Space Telescope, we can see galaxies back in their infancy 10 billion years ago. But they're still recognizably like galaxies. Can we see an earlier time, before there were galaxies? And the answer is yes. However, we don't want to look in the optical, we want to look at a different wavelength. And so the answer to this question is if we look in the millimeter wave, we can see back to a time before there were galaxies, when the universe was 1,000 times smaller, hotter, and denser than it is today. We know the universe is expanding, so when we look back in time, we're seeing an earlier time when it was smaller and hotter. And at that point, about 380,000 years after the Big Bang, we hit this wall, where basically the universe goes through this transition. Before this time, the universe is hot enough that electrons and protons are free. Okay, they're just bouncing around, and these free electrons strongly scatter light. Okay, they strongly interact with the light. So, and then after this time, neutral hydrogen forms. Those free electrons and protons pair up, and the universe becomes substantially transparent. And in fact, the photons we're seeing when we study the microwave background are basically the age of the universe. They're the oldest photons in the universe. This surface is kind of like, you can think of it kind of like the surface of a cloud. When we look back and we look at the microwave background, we're seeing through the entire universe, which is transparent. We see this surface, and then the photons bounce off of electrons. They're not destroyed, they're scattered. So it's a bit like looking at the surface of a cloud, which has got the sun behind it. You can't see the sun, and you can't see into the cloud, but you can see the surface of the cloud. So when we study the microwave background, we're basically studying this time. And this is pretty early in the early universe. If the universe today were a middle-aged adult, it's 13.7 billion years, so I scale that. When we look at the time of the microwave background at 380,000 years, that's kind of like 8 minutes after conception, okay? So you get a much different picture of what the universe looks like at that time. And then if we want to learn something about what happened to the universe before that time, we sort of have a problem, because the universe at that point becomes opaque to light, so we have to make inferences. But there's evidence that something very interesting happened at the first moments after the Big Bang, something on the order of a trillionth of a trillionth of a trillionth of a second after the Big Bang, we think the universe went through a rapid period of expansion. And I'll explain why it is that we need that. Okay, so just to catch you up to speed about cosmology. Your guys are quick studies. So the whole idea that our universe was actually dynamic, not just a static, eternal thing, really came out in about the 1920s by observations that were made by Edwin Hubble on Mount Wilson in Pasadena. And what Hubble discovered is that all the galaxies we look at are receding away from us. The universe is apparently expanding. All the galaxies we see are moving away. And this was a big surprise to no less than Albert Einstein, who had devised his theory of gravitation such that the universe would be static, he thought. And when he saw these observations, he realized that his theory was incorrect, and he had to modify his equations to accommodate this fact. So we know the universe is expanding. As we look back in time, the universe gets hotter and denser, as I mentioned, and at one point, the universe was the temperature of about the temperature of the sun in these early times. That was a prediction, and then surprisingly to some people, in the mid-60s, we discovered we can actually see the glow of that time, and that's the microwave background that was discovered 50 years ago in New Jersey. This is from Bell Labs, Penzias and Wilson. So we've known since about that time that the universe had this hot beginning, but there's this important bit missing about the very early universe, and I'll explain where that came from. Okay, so what I'm going to do next is I'm going to show you a map of what the sky looks like if I look in optical wavelengths. So this is like a map of the surface of the Earth, right? You've all seen these projections. If I took a map of the surface of the Earth and flattened it out, you'd have this with the equator running across the middle of the map. This is like the same thing, except instead of looking down on the Earth, I'm looking up, and I make a map, okay? And this is what you see here at optical wavelengths. It's in galactic coordinates, so that big stripe across the middle is the plane of our galaxy. And then there's, if you zoom in, you see lots of stars and some dwarf galaxies nearby and further galaxies, blah, blah, blah. Now, if I make this same map in the millimeter, what do you think I'm going to see? This is what we see. This is real data. This is what the sky looks like in the millimeter. This is all coming from the microwave background, and it is all exactly the same temperature in every direction we look. Well, not quite. There are small deviations, about 10 parts per million, but the first picture is that everything is just completely the same. Well, that's interesting. And this really bothered cosmologists. In the mid-early 80s, this was really causing intellectual difficulty. And the reason is according to the standard cosmology of the time, the theory of the time, if I look at this region of the universe and I look at this region of the universe, they have never talked to each other. They've never communicated. The photons, the light from this region of the universe is just getting to me now, and from this region of the universe is just getting it to me now. The light hasn't gone past so that these guys can talk to each other and make sure their temperature's the same. So how do you do that? How do you get the same temperature to 10 parts per million? The analogy I make is it's a little bit like, I'll tell you a story. Imagine I'm a fly, and I fly into this room, and there's all these people sitting here, and I'm a curious scientist fly, so I fly around and inquire and find out things. And what I learn is that among all the other interesting things that are going on, everyone's drinking a cup of coffee. And because I'm a physicist fly, I go and I measure the temperature of their coffee cups, and they're all the same. They're all the same temperature. They're carrying around coffee, and it's slowly cooling down. And this is really bothering me. I mean, how did these people all get together and set the temperature of their coffee to be exactly the same? It's really bugging me. Well, the answer to this is that before I flew into the room, there was a coffee break. And all this coffee that people are carrying around came from a big pot of coffee, which is all at the same temperature, okay? They poured out their coffee, and that's the reason. That all the coffee was in the same place. It was all causally connected at some point. And so the solution to this puzzle on the cosmological scale is kind of similar. It's to say, yeah, those two regions of the universe are really far apart, but there must have been an earlier time that we can't see, that they were all connected, all causally connected. And so this theory, which is really remarkable, is called the theory of inflation. And I love this plot. This is a real physicist's plot. This is the trajectory of the universe, and we're at the far right-hand side here. The x-axis has got 50 orders of magnitude on it in time. And so the surface of the microwave, we're at the very right, the surface of the microwave background is that red line, and everything else there's happened before. And on the y-axis is the size of the visible universe, and it's got 100 orders of magnitude on it, okay? And the theory of inflation says that in the very early universe, something happened that caused an enormous exponential expansion of space-time. And that expansion, and this is allowed by Einstein's equations, that expansion happened so quickly, it took two observers who were all nicely in causal contact and flung them apart faster than the speed of light. Space itself expanded faster than the speed of light. So the idea is our entire observable universe came from a subatomic volume, all causally connected, and then this weird process of inflation happened that flung that all apart. And now when we look at the microwave background, we look at these two regions of the sky, they know about each other because they were back in contact way back when at the beginning of the universe. This theory also says, or implies, that the universe we see today, grand and enormous as it is, 13.7 billion light years in radius, is only a small fraction of the total universe, because very likely there was a region beyond what we could see at this earlier time that was flung apart. So the universe is probably much larger than what we can see. And so this kind of solves that problem. And you might say, well, how do you have this process happen? But as I said, Einstein's equations allow you to do this. You need to have some weird matter energy with a repulsive effect, okay? But that's not impossible. And if you could have this substance, you can get an exponential expansion like that. And maybe the universe is kind of having a similar effect, much more gradual, today. So how do we test a theory like this? What kind of predictions does it make? Well, one way to look at this, you can do this experiment at home if you want later on. Inflation is a little bit like you take a resistor, and that resistor has got thermal noise in it. So, just random variations that are set actually by quantum mechanics. Okay, and then you have a very low noise amplifier. You can hook that up to the resistor, and you can actually hear those quantum fluctuations. It's white noise. You've heard of the term, just kind of a hiss. And you can hook that amplifier up to a speaker, and you can hear that white noise. And then if you want to go one step further, you can take that speaker and you can put it up against a bowl of Jell-O and see how the Jell-O shakes. Okay, and the Jell-O has particular frequencies that'll resonate with this broad spectrum. And so when we study the microwave background, we're kind of studying the Jell-O. We're seeing how the universe responds to what we think is an earlier set of fluctuations that are set up by inflation. So if we can understand the Jell-O, perhaps we can say something about the initial spectrum of set up by inflation, which in this case is really the amplifier that blows up these minute quantum fluctuations to macroscopic scales. The analogy here in the case of the universe is inflation takes quantum mechanical fluctuations, okay, the smallest noise structure we know in physics, and blows them up to enormous scales. When we look at galaxies and clusters of galaxies, there's a structure associated with that. That structure, on the largest spatial scales, were born from quantum mechanical fluctuations. Okay, that's a pretty profound idea. But that's basically one way to get an inflation. Okay? And what this looks like is if I now go back to that millimeter wave map of the sky, the orange thing, right? If I take off the constant signal and the fact that we're moving with respect to this background, take off that component, I can now start to see the tiny fluctuations and variations that are real in the microwave background. And this has turned into something of an industry. There's actually been 3 generations of satellite experiments to go and measure the spatial structure that we see in the microwave background. This is the most recent and best measurement from a European satellite with NASA participation called the Planck satellite. And the structures you see here, as I said, they're tiny. They're tens of parts per million of the total signal. But all those fluctuations are real, okay? And they're all resolved. You can see there's sort of a characteristic size scale to this image. The beam of the satellite itself is much, much smaller than this. All these structures that we see here are real and mapped out. And the short answer is when we look at a map like this, the basic picture is consistent with the idea of inflation. And just to give you for instance, you can kind of pick out a characteristic size scale in this map. That size scale, we think we know the size of it. And so when we make a map like this, we can actually measure the geometry of the universe. And the geometry, the answer is, the universe is almost precisely flat in its geometry as well as we can measure it. That's a prediction of inflation, because it says whatever shape the universe was in, I'm going to blow it up, and it locally is going to look pretty flat. Okay, so that's one example. So the basic picture of inflation, this crazy idea, is holding up. We have lots of evidence that a process like that happened. But let's say we want to learn more. What was the strange substance that drove inflation? So now this is starting to depend on what we believe inflation was produced by. So I mentioned that inflation blows up quantum mechanical fluctuations and makes these overdensities and underdensities from these quantum mechanical fluctuations. So you can think of these overdensities and underdensities sort of like a sound wave, okay? You've got regions which are denser and regions which are rarefied, okay? Now we know about that, we've measured that really well, but maybe inflation also does something else. Maybe there's not only quantum mechanical fluctuations, there's quantum gravitational fluctuations, okay? So physicists have long pursued this idea that maybe there's a connection between quantum mechanics and gravity. We don't really have a theory of this. But if there is, inflation would take those quantum gravitational fluctuations, it wouldn't make something like these density fluctuations. It would make a background of gravitational waves. And that's different. And the way to get at that signal is to make a very precise measurement, and I'll explain a little bit more, of the polarization of the microwave background. So this is the signal that we've been working so hard for well over a decade to go after with an experiment like BICEP2. Okay, so just to basically summarize the picture here, we're looking at this surface of last scattering 380,000 years after the Big Bang, but we want to learn about inflation way at the very beginning, the first moments after the Big Bang. So we have to make some inferences. But inflation sets up both this sound waves and maybe at some amplitude gravitational waves. And if we can detect the polarization in the background, we kind of short circuit this path because we're seeing the influence of gravitational waves that produce this polarization signal, and we're learning something about what happened way back right after the Big Bang. Okay, so I have a couple of theorists here that are going to explain more about how this works.
Yeah. Now, seriously, I'm just curious, and I think a lot of us are, what do you seriously like to read, like just like in the book world?
With science.
Really? Really?
Fascinated with science. It's incredible. Have you heard about the new brain theory?
No. Whose brain theory is this?
It's Stephen Hawking has been...
Stephen Hawking?
Yeah, talking about this new brain theory about the universe and opposed to the Big Bang theory, and they're coming out with some new concepts. It's really exciting.
And you actually read about...
Iperiodic universe. Have you heard about this?
The say it again?
It's very difficult to say. The Iperiodic universe.
Wow. That's amazing that you're reading that stuff.
Well, the model we have now, Conan, is based on the idea that our Big Bang universe was created from the collision of two three-dimensional worlds moving along a hidden extra dimension. But conceptually, the Iperiodic model is very different. There is no inflation or rapid change happening at all. The approach to collision takes place very slowly over an exceedingly long period of time. It's quite fascinating that the rapid change and very slow change can produce nearly the same effects. The difference results in one distinctive observational prediction, though. The inflationary cosmology predicts a spectrum of gravitational waves that may be detectable in the cosmic microwave background. The Iperiodic model, however, predicts no gravitational waves. Effects should be observable in the cosmic microwave background. And I'm just so relieved by this because I've been... No, really.
Incredible.
Okay. So I think what Jim was saying is that if we can see the polarization of the microwave background, we can say something about what happened in the early universe. Well, I'm an experimentalist. I like to build things and make measurements. And this is a program that we started at Caltech and JPL around 2001. And the idea was we were really taken with the notion that we could say something about the early universe with a very specialized experiment. We just had to build something that was super sensitive to polarization, which was kind of a new thing. And so we built this dedicated line of experiments that were going to go out and hunt for this thing. I had a colleague who liked to call this wild goose chase. He was very proud of this fact, and he would say this in front of national funding agencies. And anyways. But he thought it was a great adventure. And so we're practical folks, so we started this in stages. What you see here is basically a small telescope, and that architecture stayed the same, but we have been slowly building up sensitivity by new detector technology developed at JPL to get the sensitivity we need to make this measurement. So the first stage is called Bicep 1. That's California, by the way. And then a second experiment which just has a new detector array, which gives it 10 times more speed. So it takes 10 times less time to make a measurement, otherwise the same experiment called Bicep 2. And then currently our experiment, that's the South Pole, is the Keck array, which basically has 5 telescopes. So it's altogether about 50 times faster than our prototype. And as I mentioned, our secret formula here is really young scientists. This shows some of the graduate students that have made their thesis on this project. Many of them are at Caltech, and a similar number of young postdocs. So now what we're trying to do is extremely difficult experimentally. We're trying to measure a minute signal, and the level of the signal is, if we had 30 million photons, the difference in the polarization is about one of those photons, okay? So we're looking for a polarization signal that's very, very tiny. Now, where does the polarization signal come from? So the basic idea is that electrons, at this early time when the universe is a plasma, they scatter light. And if you're familiar, say, like looking at the surface of a car hood with the sun shining on it, you know that that scattered light is very polarized, which is why people wear polarized sunglasses. The idea is kind of the same here with the background. That scattering process makes a polarization signal. But it's driven by some temperature difference at the time that this process happened. So if I have a density wave, I told you inflation sets up a density wave. That density wave has compressions where the plasma heats up, and it has rarefications where it gets cooler. So then if I'm an electron, I see this temperature difference, and I can scatter that light and make a polarization signal. It's a much smaller effect than the the temperature itself. So that's a density wave. What about a gravitational wave? Well, a gravitational wave is different. Density waves, like a sound wave, right? Space is kind of compressing and rarefying. Gravitational wave, in case you're not familiar, as a gravitational wave is propagating, let's say it's propagating in this direction, it stretches space in one direction, it squeezes it in the other. So if I had a circle here, say, and a gravitational wave is going this way, I would see that circle stretch and squeeze as the gravitational wave went by. And that's a different effect that stretching and squeezing then can produce, as it turns out, a distinctive polarization pattern. And the key here is the pattern. So if I can make a polarization map, and I can break it into two parts. So one part, called an E mode, has a pattern that looks, radial or tangential. And the key here is that if I take that pattern and I put it in a mirror, it doesn't change, okay? And then I can also look at a part called a B mode part, and those are those swirly patterns. And those swirly patterns have the property that if I put them in a mirror, they change sign. Just like if you're looking at your right hand in the mirror, it looks like a left hand. And the important point here is that density waves don't have a handedness. They don't know their right from their left. So they can't make anything but E modes. However, if we see this twisty pattern, this B mode pattern, that's something with a handedness. Can't be a density wave. Well, gravitational waves do know their right from their left. In fact, there's right and left-handed polarizations with gravitational waves. So if I see a signal like that, it's not something in the standard cosmology model. It's an indicator of something non-standard, like a gravitational wave. Okay, sorry, this is the most technical plot, but I have to kind of give you the context. So this is a power spectrum. Basically, it tells you the amplitude as a function of spatial scale. So on the y-axis, on the x-axis, that's the size on the sky. So very large sizes are at the left of this figure, and very small sizes are at the right. And the y-axis is kind of the total amplitude, okay? And so when I make a map, I can make a figure, turn it into a figure like this, which tells me the amount of structure at different spatial scales. And the signal we're looking for is this dash signal. And we have no idea what its amplitude is. We kind of know the shape, but the amplitude could be anywhere in there, or it could be off the bottom of the chart. And these show what the measurements look like kind of December 2013. And they're all upper limits. There's no detections. One key fact about this is that if we want to study the, for a gravitational wave signal, if we want to make a measurement, that peak signal is about on a scale of about 2 degrees. Okay, so that's 4 times bigger than the full moon. It's not a fine structure. It's big on the sky. And so what that means is we don't need a big telescope to make this measurement. Small telescope will do just fine, thank you very much. Okay, so the amplitude of this signal was unknown, but we were bold and decided to dedicate many years of our lives and graduate student lives. And the amplitude here is the wild goose that we were pursuing. Okay, so I'll just tell you a bit about the parts of the experiment. As I said, we don't need a big telescope. We realized a small telescope would be just great. So we have a novel design. Well, maybe it's not so novel. It's kind of like a spyglass that is similar to the telescope that Galileo used, except while it has a small aperture, it's designed to collect an enormous amount of light. The focal plane, which gathers all the light, is the same size as the primary mirror, basically. Okay, so it means it has an enormous field of view. We're gathering a lot of photons in spite of the fact that it looks fairly humble and small. It's actually quite powerful. And once you embrace this idea of building a small telescope, there are many advantages. One advantage is I can take the whole telescope and I can cool it to 4 degrees above absolute zero. I mean, one of the problems we have is that everything we look at emits microwaves, so we want to minimize that emission. Well, I can take this whole telescope and cool it to 4 Kelvin so it doesn't emit very much. That's a nice advantage. I can also take this small telescope and I completely spin around its axis to take out any polarization in the telescope itself. That's pretty hard to do with a big telescope. So, this is a very specialized thing, but there are many advantages for doing it this way. And finally, the business end of this experiment is our focal plane. That's where we detect the microwave background photons themselves. And in order to get the ultimate noise performance, we cool our focal planes down to just 1/4 of a degree above absolute zero. And in the middle of our project, we had this huge architectural change. So the first stage of our experiment looked pretty conventional. We took this novel telescope and we used a conventional focal plane. This is not so different from the focal plane that went on the Planck satellite, which we built the detectors for. And the detectors here are pretty similar. But we realized that we really need to start mass producing detectors to get the sensitivity that we need. And so we came up with this basically printed camera approach where each of these pixels made from discrete millimeter wave components were basically mass produced with a lithographic printing process, a very specialized one. And that gives us many more detectors, and actually, as it turns out, those detectors work better. So the net is we can do this measurement 10 times more quickly. Just to highlight the differences, here I've shown the BICEP 1 focal plane, which is sitting in my office at the time, and one wafer from BICEP 2. And that one wafer has got more power than the whole focal plane, and you can see the dramatic size difference. And these are manufactured at a specialized microlab at JPL. This is basically a research lab, but it has kind of the similar equipment that are used to make computer chips, for example. But for specialized things for NASA. And that's Tony Turner who makes the magic happen. The basic idea here is that we have this printed antenna, and you can think of it like, as I said, it's kind of like a printed camera. It serves as the lens of the camera. It focuses the light. It works in 2 polarizations. That focused light is taken to a little suspended island where the power is turned into heat, okay? And the island is actually freestanding on little tiny dinky legs. The legs, which are just kind of off the end of that picture, just 1 micron thick and a few microns wide, basically hanging out in free space. It's thermally isolated, so when the microwave background power turns into heat, it heats up that island, and we have a sensitive thermometer that measures the power that tells us how much power is landed on the device. This is a classic kind of detector called a bolometer, except it's now mass-produced, and not only do we mass-produce the detector, but we actually kind of, as I said, mass-produce the lens and the filter of a camera as well. So this was a big push. It took us the better part of a decade to get technology that worked. And when it did work, the first thing we did was go out and put it into BICEP 2. The second part of our experiment is to go to the best site in the world for making these measurements, and that's the South Pole. This is what the South Pole looks like in the summer. This is a view from an airplane. It may interest you to know that there's been a continuous US presence at the South Pole for more than 50 years, going back to the Eisenhower administration. And when I say continuous, I mean there's been a resident person there the whole time, including the winters. And actually it was started out as a Navy base, of all things. And what you see here is the runway. Almost everything at the pole has come in on a ski-equipped LC-130 aircraft. This is sort of the flying equivalent of a garage, but they're very robust, reliable aircraft. They land on this unimproved runway and bring in all of our supplies during the summer. To the left of the runway, there's the main station where people live, and to the right is the dark sector lab where our experiment resides. And every day, we walk about half a mile from the station out to the lab and back. And in the winter, when it can be colder than -100, our wind rover walks half a mile from the station and services the experiment and walks back. The South Pole is sitting on top of 2 miles of solid ice. It's at an elevation of about 10,000 feet. And the reason it's a great millimeter wave site is that it's very dry. The problem with the Earth's atmosphere that it makes it difficult for millimeter wave observation is really water vapor in the atmosphere. The South Pole is very dry. It's also very cold. And you may know if you take food and put it in a microwave, the reason it heats up is because the microwave's getting absorbed by the water in your food. Now, if you take something out of the freezer, put it in the microwave, it doesn't heat up as quickly. It takes a lot longer, and that's because ice doesn't have the same properties. Well, in a similar way, because it's so cold, the air can't hold very much water vapor. It turns into ice and snow. So that's why we're at the pole. Another aspect is that actually it's a very easy place to work. The facilities there are great. And this is our experiment going in. You can see this is the telescope mount where our experiment resides. It's going inside a building. And through hard experience, it turns out that if you want to operate a telescope successfully at the South Pole, the key is to put it inside. They don't do very well outdoors. And so we took that lesson to heart. All the moving parts of our experiment are inside the building. And the green thing you see at the bottom there is a Gore-Tex weather seal that seals up our experiment. So just the nose of our experiment looks out into the environment. The pole has great logistical support. Most of the people down there during the summer, and typically there'd be 250 people, are really there to support science, not doing science directly. And if you give them free t-shirts, they'll do amazing things for you. So this is the loading crew that had a big role in installing our experiment. Once the experiment's installed, you kind of can see here, we're standing on the telescope mount. The actual telescope is you can just see the bottom of it. It's sort of sitting up there in the ceiling, and it's looking out into the environment. Now, just to get you oriented, I have a little 3D picture. So this is what we hope a CMB photon last sees after its 13.7 billion years, which is the aperture of our little telescope. So the black thing is a baffle at the nose of our experiment looking out. And this was taken from a kite by our winter rover right before sunset. And if I look up there, well, there's a big telescope. That's the South Pole 10-meter telescope. You can see kind of the sastrugi, kind of ice dunes that form up there. There's the sun just about gone down. And now you're looking across the airfield out there over to the main station. And so that's what our experiment actually does. It looks out of the roof. Okay, and one key to success here is that we have to have someone who operates the experiment during the winter. Once the temperature gets down below -50, there are no planes in and out. And typically that means between about February 15th and about October 15th, there's no way to get in or out of the station. You are there. Typically now, the station runs about 60 people. And so for our first season, we left one of our postdocs who wanted to do this. And this is the last plane going out. And so after this plane leaves, our postdoc is left to run the experiment. This is what the pole looks like at night. Of course, the sun goes down for 6 months. We told our winter rover it was just one night. And there's aurora that pop out. And you can see the plane of the galaxy. It's very pretty. And with the air temperature getting lower, you really don't have much water vapor. The data from the pole have really been spectacular. Now, the other thing is we don't want to stress our winter rover out. And so the experiment from the beginning was really designed to run pretty much as automated as we could make it. some human intervention is required, but we want to keep our Winter River happy, if not sane. And then in parallel, while that BICEP 1 was running, our guys, these are some of the postdocs and students at Caltech, were developing these new focal plane sensors. This is a picture around the 4th of July, so they made an American flag with duct tape on the cryostat. And then once the focal plane was ready to go, down it goes to the pole. So this is Justice, one of our students, and you can tell this is not at the pole because he wouldn't be wearing so little clothing. This is at McMurdo on the edge of the continent. This is the direct flight that takes you to the pole, and the focal plane sitting there in the Pelican box. And here's the new experiment, BICEP 2, going together. You can see lots of concerned people on the floor. This picture is John Kovac here, professor of physics at Harvard, developing novel cleaning techniques. And the guy behind him is our tech, Phil Wilson, who knows better. And here's the experiment going together. This shows some of the summer activities we do testing the experiment. Summer is really our time for calibration, changing out detectors. We do our observations in the winter, by and large. And then now we've been building this more powerful experiment called the Keck Array. There are actually 5 telescopes that go in this barrel once the people leave, and you can kind of see the scale of this experiment. And there are some of the barrels going in. Each one of them is basically equivalent to BICEP 2, so this experiment is 5 times more powerful. Another key is to observe a region where we don't see too much emission from our galaxy. It's kind of a curious fact of nature that the galaxy is so dim in the millimeter wave that we see the microwave background and hardly don't see the galaxy at all. But now that we're looking for these tiny polarization signals, we start to worry about the galaxy. And the galaxy can have polarized emission. So we picked this field here where we don't see much emission from the galaxy. The red stuff is the plane of the galaxy. You can see it's boomingly bright. We've chosen this dark region that doesn't have a lot of millimeter wave emission from the galaxy. And then finally, we want to just pound away on this region as long as we can. Okay? So we've been observing really since 2006, pretty much without interruption. And it's now 2014, so we've built up basically 8 years of data. And the way the observations work, we call this relentless observing. And the reason for that is that another nice thing about the South Pole is that we don't have this problem with our region setting like we have at mid-latitudes. If we're observing some region of the sky, it just goes around in a circle, and we can observe it all the time. And so that's what we do. This is a time-lapse video, and if you look, you can kind of see the plane of the galaxy slowly rotating. That gives you some idea of the speed here. And you'll see some aurora. Maybe you'll see some streaks going across. Those are satellites, in a polar orbit. And what we do with the telescope is we basically scan back and forth and observe our region 24 hours a day, 7 days a week, 365 days a year. Well, not quite. We just observe during the winter, but pretty much uninterrupted is all we want to do is just sit there and observe our region. And sometimes we see these beautiful aurora, but they don't really affect our observations. So with BICEP 2, after just 3 years, we produced the world's best polarization map of the microwave background. We work really hard on this. We're really excited. It really is, there's nothing like it. And if we took all of our data and make a map of the polarization, this is what we see. Now, the map's kind of tapered here at the edges. Okay, but look at the middle. That's the polarization signal. And this signal's tiny. It's much, much smaller than the temperature variations. And by visual inspection, we can also see that almost all the signal here is this E-mode polarization, which is cool, but it's not really the signal we're going after. The E-mode polarization is basically related to the density perturbations. We want to see if there's a B-mode, this twisty pattern. So we can mathematically take this map and we can ask how much of that is B-mode. So if I keep the same scale and ask how much is B-mode, That's what it is. That's the B mode component. Really small, okay? All right, but I can expand the scale, and now this is the B mode component. And it has this, it's only this twisty component, okay? And the amplitude of this signal is actually pretty big. The structures you see here are above the noise of our experiment, and substantially so. If it helps the eye, I can colorize them. So the colors here show the amount of clockwise, which would be blue, and counterclockwise, red, twisting in the B mode pattern. And as I said, this amplitude is actually pretty big. It's not instrument noise. It's a big signal. And that was a serious surprise. And we announced this once we were finally sure that our measurement was reliable. We announced this to the world in March. And here's where this is why I showed you the power spectrum before. The black points are now our data. And you can see a couple of things. One is there's this bump on the dashed line that's very clear in the data. And the statistical significance of that bump is large. There's only like very tiny chance that that could just be noise. It's a big, big signal. You can also see we're way below any of these other measurements. I mean, this experiment is really the first to get down to this level. So that's very, very exciting. So now, is this polarization signal real? Well, one of the things is because we have these multiple phases of our program, we can check the signal that we measure in the 3 different ways that we've measured it, with bicep 1, with bicep 2, and with Keck. We can say, is that signal consistent? And this is one of the things that convinced us internally that, yeah, this is real. And when we do that comparison, we see the same signal 3 different ways, measured with a different instrument, different time, and in the case of bicep 1, with a very different way of detecting light. And that bump is very, very reproducible. So we have to ask ourselves, is this really real? And I'll be brief. So the 3 possibilities here, is it noise? No. We don't think it's noise. The size of the signal is very statistically unlikely to be just noise. And could it be instrumental systematics? Again, no, we don't think so. We've cut up our data many ways, do many tests, but also we see the same signal between the 3 experiments. I mean, it really there's no instrument systematic we can think of that would do this. So we really don't believe that's the case. And this is why we came out with the result, because we're like, at this point, we really believe our data. Then finally, could this be the galaxy? Well, the amplitude of this signal is pretty big. And so when we came out with this, our understanding of the galaxy would indicate you wouldn't expect such a big signal from the galaxy. But it's a serious question. So what does the galaxy look like? Well, one of the keys is that the galaxy has 2 flavors, basically, of polarized emission. It has something with a very red spectrum, which is due to electrons spinning in the magnetic field of the galaxy, called synchrotron. That has a very red spectrum. You can see that line there going up towards lower frequencies, getting rapidly brighter. The CMB, if the signal's coming from gravitational waves, we know the spectrum of the CMB really well, and that's the red line. And then finally, the galaxy has dust that's in it, heated up by starlight. That dust can have a polarization. And that signal's very blue. It's rapidly rising towards short wavelengths or high frequencies. That's the green. So we can constrain the galaxy in multiple ways. And one of the best ways, as I'm alluding to here, is to make the measurements at different frequencies. See if this signal is just the CMB. Well, here we have a bit of a problem. Most of our data is coming at 1 wavelength, 2 millimeters. We have some data at longer wavelengths, but mostly our information is coming at 150 gigahertz on this plot. Now we can exclude synchrotron, There's data from a satellite called WMAP, which measured at very long wavelengths. And we look at the data in our region, we don't really see anything, and we don't see anything in correlation with our experiment. So it really doesn't look like we're seeing synchrotron. What about dust? Well, dust is kind of a tricky one. There isn't, right now, good polarized data on dust. We have models, we have our color measurement, we have the morphology of the experiment. So we can say it seems unlikely from our data that the signal's all dust. But until we have hard data on the polarization of the dust, there's still that possibility that there's a, it could all potentially be dust. And so to answer this question, galactic foregrounds, we can rule out synchrotron, but we can only say that the data disfavor dust. We think it's unlikely that the signal's all dust, but we can't completely exclude it at this point. Well, enter a space experiment called Planck again. And Planck is really the ultimate for constraining the galaxy. It has 9 frequency bands, so we measure the galaxy at multiple frequencies. We can really say quantitatively how much of this emission is coming from the galaxy. And this shows a bit of the design of Planck. There's actually 2 instruments, and there's the launch. It's a European project launched on an Ariane 5 from French Guiana, 2009. Project's now done, all the data's collected, but the polarization data haven't been released. Okay, they're coming out in the fall. And Planck, by the way, is also just a technical tour de force. I mean, this is an amazing instrument, if I do say so myself. The ultimate temperature the detectors are at on Planck is at 0.1 degrees, above absolute zero. These detectors are basically limited just by the noise from the microwave background itself to good approximation. So this is really an awesome instrument. But you'll notice, by the way, that detectors here are outdated because it's a space experiment. With BICEP2, we were able to leap ahead a generation of detectors. And that's really why we get this advantage, is because we're able to put the latest detectors into the BICEP2 focal plane. Okay, so this is a work in progress. We've just signed a memorandum of understanding between BICEP2 and Planck that we're going to collaborate jointly to do this. And the combination is really the best of both worlds. We get the unprecedented sensitivity of BICEP2, and we get the unprecedented frequency coverage of Planck. And you really don't get that until you put the 2 experiments together. You don't get that with one or the other by itself. So this is really exciting. We're really just right now in the midst of it. Another aspect, by the way, is that the Keck machine has been running for 2.5 years. It's more capable than BICEP2. And it has data at longer wavelengths. So that's coming as well. We put those in just this year. The data looks great, but we're still working on it. So all this stuff between us and Planck and with our improved data from the pole is really going to tell us the answer. And you should look out for an answer coming around November this year, hopefully. Okay, so in conclusion, what does this all mean? Well, first of all, let's not get too excited. We have to confirm this signal, and we have to rule out the galaxy. But what we've seen is that there is a big signal there. We want to investigate it. It's very exciting. It really looks like it could be cosmological. If it is a gravitational wave signal, that signal really tells us the process that powered inflation itself. First of all, there's this deep connection between gravity and quantum mechanics, just from the fact that the signal's there. That's pretty cool. That's physics we don't really understand. And it's telling us, some models of inflation can do this, but most of them can't. So it's discriminating between models of inflation. It tells us the energy scale that inflation happened at. And I wrote a number here. It's a big number. But just to put this in context, the physics, we should look at this number compared to what we can get at from particle physics. And the energy scale here is much bigger than any particle physics experiment that we can build on Earth. You've heard of CERN, this enormous particle accelerator. This is orders of magnitude above any energy that CERN can reach. So we're learning about new physics as a result of this. And that energy scale is very suggestive. It's suggestive of a scale called grand unification, when 3 of the 4 forces of nature had the same force. So maybe, as theorists have maybe suspected for some time, maybe going from a unified force to the 3 forces, that transition, maybe that's the key. Maybe that's the mechanism that powered inflation. And then finally, what if this signal is real? Well, there's a lot more we can learn about from this signal and about inflation. That's really exciting because it's a big signal. Now we want to learn everything we can about it. So let's not get carried away, but if the signal is real, we're going to want to measure it over the whole sky with a new satellite experiment. And there is something like this in NASA's roadmap called the Einstein Inflation Probe. So that's my talk. Thank you very much for listening. I can do questions if anyone has one. Right. So the question is where does all the mass come from if you start with a point? Well, that's a good question. I can answer that with another question, I guess. So some might say, well, it's from the Big Bang, this initial event. But inflation itself actually kind of acts like a Big Bang. It provides this impulse. There's a lot of energy associated with it. What happened before inflation? Was there a Big Bang? Sorry. Yeah. Right. Well, I think for millimeter wave observations, the pole's the best place. It's certainly a lot better than Hawaii from my experience. And there are experiments that are running in Chile. And so an interesting question is, the pole is nice because you can go deeply in this one region where you can't do that in Chile. But maybe we'll get to a point where we want to map so much sky that that'll actually become a limitation. And then Chile would become a good place to observe. So Planck maps the entire sky. That was the original design. So our patch is just about 2% of the sky, but Planck covers it because they cover the whole sky. Right. Yeah, so what happens is as I alluded, we're looking at this time, 380,000 years, the universe, the free electrons and protons pair up, become neutral. Okay, so there's this period of the dark ages after the Big Bang where you've got neutral hydrogen. And then, it's not neutral now, and it's not neutral back to, redshift of 6, so like 12 billion years looking back, it's all ionized. So something ionized that gas, and that's thought to be the first stars, which end the dark ages. So the fact that the gas is ionized now means it's not quite transparent. It does affect the microwave background. So one of the first data points we have about when this end of the dark ages happened actually comes from polarization in the microwave background. No, we were set on this wild goose chase by theorists who came up with the idea of looking for this B-mode signal. So theories of inflation have had a gravitational wave component, maybe going back to the early times of the theory. But in the late 90s, there were several theorists who figured out that by making these polarization measurements, you could actually kind of tease it out. So those papers, that idea really emerged in the mid to late 90s, and pretty quickly thereafter, because those guys were down the hall from us, we went off and we built our experiment.
Thank you very much for